Okay, so I'll start. Right. Welcome to the week 7 live session where we will be talking more about different kinds of spectroscopy. So, just to recap what we had learned in the previous class, spectroscopy is the study of how different forms of electromagnetic radiation interact with atoms and molecules. So, if the radiation falls on the surface and passes through without any deviation, it is called transmission. If it falls and reflects back, that is reflection. If it passes through the surface but after a change in angle, that is called refraction. Diffraction happens when the radiation passes through the slit and then is scattered equally in different directions, and the net scattered wave results from constructive interference, resulting in increase in intensity, and diffraction is used in X-ray crystallography. Absorption is when the surface absorbs the energy of the electromagnetic radiation and can get heated up. And scattering is when it is like diffraction, but scattering is in random directions, while in diffraction, it is scattered in such a way that all the scattered waves undergo constructive interference. So, optical instruments called spectrometers reveal as a series of specific wavelengths or frequencies the light energies that are absorbed or emitted. And from these wavelengths or frequencies, a spectra is formed, and that gives us information about the atomic and molecular structure of substances. It is kind of, the spectra is kind of like the fingerprint of a substance. Like a person has a unique fingerprint, each compound also has a unique spectra. Like, you can see different kinds of compounds here, and this is the NMR spectra that we had learned about last class. So they are simply differing in the functional group that is attached to benzene. So this is plain benzene, this has an aldehyde functional group, this has an alcohol functional group, and according to that the spectra is varying. So clearly the spectra is a fingerprint or an identifier of the compound. So, in the history of spectroscopy, we had learned in the first class about how white light can break into its component 7 colors when passing through a prism. This was found by Isaac Newton in the latter half of the 17th century. Then Einstein had proposed the particle nature of light, and now we know that light can exist both as a wave and as a particle. And when it exists as a particle, the energy of each particle can be written as E equal to h nu. So this is the dual character of light. Uh, After that, scientists had observed dark and bright light lines seen in absorption and emission spectra, and these lines were characteristic of the internal makeup of chemical elements. So they had observed that there can be two kinds of spectra. One in which there are dark lines like this, and that happens in absorption spectra. So suppose white light is falling on an atom, certain those radiations in white light will be absorbed, which correspond to the energy difference between two energy levels. So that particular radiation is absorbed, that will be absent from the spectra. That is, so suppose white light passes through the substance, two particular wavelengths are absorbed. So those two particular wavelengths are absent in the spectra since they are absorbed, and they appear as the dark lines. So here the dark lines correspond to the 3 to 1, which is level 3 to level 1, and 2 to 1, which is level 2 to level 1 absorptions. Because these two particular wavelengths are absorbed, they appear in the spectra as dark lines, and this is an absorption spectra. In emission spectra, what happens? Only that wavelength which is emitted is observed as bright lines, and the rest of the spectra remains dark. So after absorption, the atom must come down to the ground state, and that forms the emission spectra basically. So whichever wavelength was absent in the absorption spectra, that wavelength is observed in the emission spectra. When the molecule comes down from 3 to 1, it can come down in one step, in which case you will get a 3 to 1 line, or it can come down in two steps, 3 to 2 and then 2 to 1, in which case you would get two lines. So from the absorption and emission spectra, it was proposed that only light of certain wavelengths will be absorbed, which correspond to the energy difference between two energy levels. This also proves the particle nature of light, because only when the particles have a certain energy of h nu can the atom be promoted to the upper energy levels. Then just to recap what we have learned about the electromagnetic spectra. So in the electromagnetic spectra, there are many different kinds of electromagnetic waves, varying from radio waves, which have the largest wavelength and so smallest energy. Eventually, there is microwave, infrared, visible, ultraviolet, X-ray, and gamma rays, in which gamma rays have the shortest wavelength and so highest energy. We had learned that X-rays were used to study about the proteins and different biomolecules, and radio waves were used to study NMR. So in spectroscopy also, there are different kinds of spectroscopy, like IR spectroscopy, which uses the infrared region, or UV-Vis spectroscopy, which uses the ultraviolet region. So different regions of the electromagnetic spectrum are used in different kinds of spectroscopy. Just we will go through shortly the use of the different kinds of waves. So radio waves, as you know, are used by radio stations, and they are also emitted by stars and gases in space. And radio waves also find application in NMR. So we had learned about the two spin states in NMR. And for the electron to be promoted to the higher spin state, the energy required is that of radio waves. Microwaves are used in cooking and also by astronomers to learn about the galaxies. Microwave finds applications in rotational spectroscopy. We will learn about this later, that is internal rotation within a molecule, and to detect that rotation, microwave spectroscopy is used. In infrared spectroscopy, the electromagnetic spectrum region falling within the infrared region is used, and this region is also used for Raman spectroscopy. Visible region is the part that is visible to our naked eyes, and they are involved in the electronic transition in the molecule. So from one electronic state to a higher electronic state, the energy required is that of visible light. UV light, as you know, is harmful when absorbed by the skin, and it is also used in fluorescent tubes. UV lights are used in UV visible spectroscopy, and they result in electronic transitions of the molecules, and so it is also called electronic spectroscopy. X-rays can be used to view the bones of our body using MRI imaging, and they cause transitions in the internal electrons of the molecules. If you remember, an X-ray knocks out one of the inner electrons, leaving a vacancy which is filled by the outer electrons, and that results in emission of a characteristic X-ray. So that is used in X-ray crystallographic studies. If we look at how an electromagnetic wave is developed, so all electromagnetic waves are created by accelerating electric charges. So if we consider a vibrating positive charge vibrating up and down like this in simple harmonic motion, then an electromagnetic wave is emitted from that charge. And the frequency of the electromagnetic wave emitted by the charge is equal to the frequency of the charge's motion. To create light waves in the visible part of the electromagnetic spectrum, the wavelength required is 0.4 to 0.7 micrometer. So if you look back, the range of the visible light is around 400 to 700 nanometer, or 0.4 to 0.7 micrometer. So for waves of this wavelength to be generated, the electric charge must accelerate at a rate high enough to generate these waves of this wavelength. So we know the formula V equal to F lambda, where V is the wave speed in meters per second, F is the frequency in cycles per second or hertz, and lambda in the wavelength is the wavelength in meters. So the velocity of the wave is equal to the frequency of the wave into the wavelength. Wavelength, if you remember, is the distance between two adjacent regions which have the same phase. So the distance between two peaks or two troughs. And each electromagnetic wave consists of two perpendicular waves, an electric field shown by this orange wave and a magnetic field shown by this green wave. So both these electric field and magnetic field vibrate at directions perpendicular to each other, and the direction of propagation of the overall electromagnetic wave is perpendicular to both the electric field and the magnetic field. So, like we saw that the formula for the velocity of the electromagnetic wave is V equal to F lambda. Now we know that the velocity of any light wave in space is 3 into 10 to the power 8 meter per second. And we want light in the visible range. So suppose 0.5 into 10 to the power minus 6 meter. So if we rearrange the V equal to F lambda, we will get F equal to V by lambda, in which we are taking V as 3 into 10 to the power 8 meter per second, and we are taking lambda as 0.5 micrometer, which is in the visible range. So we see that for light of visible range to be emitted, the frequency of vibration of the charged particle must be 6 into 10 to the power 14 hertz, which is a huge value. Normally, this kind of high frequency can be obtained only in regions inside atoms and molecules, where the electrons are moving very, very rapidly around the nucleus, and the atoms vibrate and oscillate very rapidly in molecules. So physically, you cannot make a machine which vibrates at such high frequencies. It is only the internal motions of the atoms and molecules which can vibrate at such high frequency and lead to the emission of visible light. So how you can create such electromagnetic waves? Basically, an AC power supply is taken, and the opposite terminals of this power supply is connected to the upper and lower arms of an antenna, and an electric current is passed through the antenna. So the accelerating electrons are moving downwards in both the upper arm and the lower arm. And so the electron is oscillating first downwards, then upwards. So the oscillation of the electron is creating an electromagnetic wave moving outwards. And the frequency of the wave will be the same as the frequency of this oscillating electron. So like this, one after another, waves can be created and they can be detected by a receiving antenna. So the principle behind formation of electromagnetic waves is the vibration of a charged particle, which in this case is an electron. So what is the mechanism by which molecules interact with this electromagnetic radiation? So in order to interact with the electromagnetic radiation, the molecule must have some electric or magnetic effect that could be influenced by the respective components of the radiation. So as we discussed, electromagnetic radiation has an electric field and a magnetic field which is perpendicular to the electric field. So to interact with the electromagnetic radiation, the molecule must have some effect on either the electric field or the magnetic field. So in NMR spectroscopy, just to recap, the nucleus has a spin, and in the absence of a magnetic field, these spins are randomly oriented. But when an external magnetic field is applied, these spins orient either parallel or anti-parallel to this external magnetic field. And this results in splitting up of energy levels. So if the spin is oriented parallel to the external magnetic field, the energy is lower and it creates the ground state. And if the spin is anti-parallel to the external magnetic field, the energy is higher and it creates the excited state. So in this case, if you supply an electromagnetic wave, the spin will be promoted, the nucleus will be promoted from the lower level to the upper level. So basically here, the magnetic dipole of the nucleus is interacting with the magnetic field of the electromagnetic radiation. And when the energy of this radiation is equal to the energy difference between the two levels, then the nucleus gets promoted to the upper level. Next, in rotational spectroscopy, we basically study the rotation of a molecule. But for this, the molecule must have a net electric dipole moment, such as water. So only if the molecule has a net electric dipole moment, then the change in the direction of the dipole moment will affect the electric field of the electromagnetic radiation, and we can observe the rotation of the molecule. Similarly, vibration of the molecule or vibrational spectroscopy uses infrared radiation, and it can only be observed when the dipole of the molecule is changing with time. Because only when the dipole is changing with time will it affect the electric field of the electromagnetic radiation. And when there is interaction with the electromagnetic radiation, only then we can observe the molecule. Electronic transitions, which is the promotion, absorption, or emission between electronic energy levels, generally occur with UV visible region of the electromagnetic spectrum. And they vary according to the geometry, size, and spatial organization of the different orbitals in the molecule. So there are different kinds of spectra. Continuous spectra is obtained when white light is passed through a prism. So as we saw that when white light is passed through a prism, it breaks up into its several components, and when all the components are present together, it is known as a continuous spectra. The absorption spectra occurs when particular wavelengths are absorbed within the continuous spectra to promote the electron from lower level to upper level. And those wavelengths that are absorbed appear as dark lines because they are not available. Emission spectra is kind of the opposite of absorption spectra. So in absorption spectra, this particular wavelength had been absorbed to promote the electron from lower level to the upper level. In emission spectra, this wavelength is emitted and is seen as a sharp line in the emission spectra. So whichever wavelengths are missing in the absorption spectra, those are the wavelengths that are visible in the emission spectra. So here you can see, so absorption of a photon occurs when the electron absorbs a photon of energy h nu, it gets promoted from ground state to excited state. So the wavelength of this radiation will appear as a dark line in the absorption spectrum. Again, when it comes down to the ground state, it emits a photon of energy of the same energy, and the wavelength of this photon will appear as a bright light in the emission spectrum. So the energy difference between the two energy levels must match the energy of the photon. So delta E must be equal to h nu. And as we saw, nu, the frequency, can be written as c by lambda, where c is the speed of light and lambda is the wavelength of the radiation. So this implies that the molecule absorbs exactly that wavelength of radiation that can promote the electron from lower level to the upper level. So technically, the absorption and emission spectra should be very sharp lines, since they are representing only a single wavelength. But in reality, what happens is that the absorption spectra appears as a broad line. So in axis here, there is wavelength, x-axis, there is wavelength, and y-axis, there is intensity. So you can see this is not a single wavelength, but a short range of wavelengths that is being absorbed. So what is the reason for the absorption spectra being slightly broad and not sharp line? So there can be many reasons. One of the reason is instrumental factor. So in the instrument, for your absorption, there is a slit through which the light is passing. And the slit is allowing wavelengths of not exactly lambda, but differing by slightly like plus lambda, plus delta lambda, minus delta lambda. So basically so the wavelength is passing through the slit can differ in a slight range of lambda. So the absorption peak, it becomes symmetry to the wavelength that is absorbed. So depending on the slit width, so here 3 examples are shown. If the slit width is narrow, a sharp spectra is seen. But as the width of the slit increases, the spectra becomes more broad and you cannot distinguish the different peaks. So here there are clear 3 peaks because there is a small slit. If there is a larger slit, the 3 peaks are merging. And here where there's a very large slit, there is one broad line. So depending on the slit width, the sharpness of the absorption spectra varies. Another factor is called a sample factor. So molecules in liquid or gaseous sample are in motion and they keep colliding with each other. So you have learned about Brownian motion, where the gas particles can move randomly at different directions. So during this random movement, they will collide with each other, and this collision influences the vibrational and rotational motions of the molecules. And this causes broadening. And the broadening, such broadening caused by the motion of the molecules is also known as Doppler broadening. So as you saw before, that the transition is not a single energy level. So you can see there are many different energy levels. So actually, when we talk about a single transition, it can occur between, suppose the atom is absorbing wavelengths lambda plus minus delta lambda. So this short range of wavelengths can allow transitions between these closely spaced energy levels. So from ground state, it can go to 3, 4, 5, 6. All these energy levels are very closely spaced. So that is why the absorption spectra becomes broadened. You can see here the absorption spectra, which is ideal, has very sharp lines. So if this is a hypothetical situation where the gas particles are at rest. So the absorption spectra from that has very sharp lines. But in reality, what happens? The gas particles move randomly and collide with each other. So there are many different vibrational and rotational motions, and that lead to the spectral lines becoming broad, as you can see in this example. The third reason is called intrinsic or natural broadening, and that arises from Heisenberg's uncertainty principle, which states that the shorter the lifetime of a state, the more uncertain is its energy. So basically, the mathematical relation is that if delta T is the lifetime of a molecule in an excited state, and delta E is the uncertainty in energy, then the product of delta E into delta T must be greater than equal to h by 2 pi. H prime by 2, where h prime is h by 2 pi. So basically, delta E into delta T is greater than equal to h by 4 pi, where h is the Planck's constant. So this is illustrated over here. So the ground state has a very long lifetime. So if the lifetime delta T is long, then delta E must be short because h prime by 2 is a constant. So if your right hand side is constant and delta t is long, then delta E must be short. That is why the energy of a ground state does not have any uncertainty. Now, as you increase the energy, the lifetime becomes shorter. So this is the first excited state. This is the second excited state. So the second excited state has short lifetime. That is, the delta t is small. So delta E must be large because your right hand side is a constant. If delta E is large, that means there is a large uncertainty in energy. So the energy level becomes blurry like this. And so when there is a transition from an uncertain energy level or blurry energy level, naturally the peak will broaden. So this kind of broadening is known as intrinsic or natural broadening. So this is a general spectrophotometer, which is an instrument that measures the amount of light absorbed or the intensity of color at a given wavelength. Generally, the UV visible spectrophotometers acquire data in the range of 190 to 800 nanometer. So spectrophotometers consist of a light source. The light source will enter through a slit. It will split into its component wavelengths using a prism, and then only only a certain wavelength will be allowed to exit through the slit. So this whole region, all these components together, the entrance slit, the dispersive prism, and the exit slit, they together form the monochromator. So we had learned during X-ray crystallography, monochromator is an instrument that converts, so if you have light of multiple wavelengths, monochromator converts it into a single wavelength light. So that is what this region is doing. Light of multiple wavelengths or white light is entering and only light of a certain wavelength is exiting. So this light of a certain wavelength or the monochromatic light passes through the sample, and then whatever the light that is transmitted is observed by the detector. So the basic components of the monochromator include the light source, the disperser to separate the light into its various component wavelengths, and the detector to detect the final transmitted light. So there are two terms associated with spectrophotometers. One is called transmittance, which is given by the equation transmittance equal to I by I0, where I is the intensity of the light after it has gone through the sample and I0 is the initial light intensity. So basically transmittance is the ratio of the intensity of light after passing through the sample and the initial light intensity. Absorbance is related to the transmittance by this formula, where absorbance equal to log of transmittance, minus log transmittance, or minus log I by I0. So these are two terms that the detector detects. The detector generally detects the amount of light that is transmitted after absorption. So how is this absorbance measured? There is a law called as Lambert-Beer's law. So Lambert law states that when a ray of monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the length of the absorbing medium increases. So if you have, so basically this was the absorbing medium. If the length of this medium increases, then the intensity of the light passing through it will decrease. So here you have a plot of absorbance versus path length. So when the path length is lower, which is this lower line, the absorbance value is also low. When the path length is higher, the absorbance is high. This is Lambert's law. Beer's law states that when a monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the concentration of the absorbing medium. So Beer's law basically states that as the concentration increases, the absorbing the light that is obtained after. So as you increase the concentration C of this sample, the intensity of the light after passing through the sample will decrease. So if you look at this plot, there are the absorbance of the same molecule has been recorded at different concentrations. So, sorry, the absorbance, this is the plot where absorbance versus concentration is plotted, and you can see it is a straight line. So, as the concentration increases, the absorbance is also increasing. Lambert-Beer's law connects Lambert's law and Beer's law together, and it says that the linear relationship between absorbance and concentration of an absorbing species is related by A equal to small a LC, where capital A is the absorbance, which we learned in the previous slide, is equal to minus log of transmittance. Small a is the molar absorptivity, also called the extinction coefficient. Molar absorptivity is dependent on the wavelength. So for a particular species, this molar absorptivity term will vary according to the wavelength of the light that we are passing through the sample. L is the path length in centimeter. This is the diameter of the cuvette or sample holder, which is the distance the light travels through the absorbing sample. So this is your path length, which is the diameter of this container. So the path length is constant when the same cuvette or container is used for the sample. C is the concentration of the sample in mole per liter. Generally, Lambert-Beer's law is used to determine the concentration of the various solutions. So your spectrophotometer will give you the value of A. From your container, you know the value of small l, and capital A is constant for a particular wavelength. So you know capital A, small l, you can find C or the concentration of your solution. So first we will start with UV visible spectroscopy. There are many different kinds of electronic transitions. So as you know, we'll just shortly go into sigma and pi orbitals. So sigma orbitals happen when there is a head-on overlap between s or p orbitals. So just 1 second, I think someone wants to enter. Right, so I'll continue. So if there is head-on overlap of two orbitals, a sigma orbital is formed. So if both of these are plus, then it is a sigma orbital or a bonding orbital. And if one is plus, one is minus, it's called a sigma star or anti-bonding orbital. So the transition from sigma to sigma star, which the sigma energy level is here, it's not visible very well in this just. So the sigma energy level, as you can see, is the lowest energy level or the bonding level. Just 1 second. Yeah, now it's visible. So pi orbital is when there is a parallel overlap. So in pi orbital also, when the phases are the same, then it is called a bonding pi orbital. And if the phases are different, it is an anti-bonding pi orbital. So in a molecule, you can have a sigma bonding and sigma star anti-bonding, pi bonding and pi star anti-bonding orbitals. There is also an orbital having the lone pair or non-bonding pair of electrons. So there can be transitions between all these orbitals. So bonding orbitals are generally full of electrons. So and anti-bonding orbitals are empty. So the transition will occur from sigma to pi star or sigma to sigma star. So from a full orbital, it will transition to an empty orbital. And there are many different kinds of these electronic transitions. But the two most common kinds are the transition from N to pi star, meaning a non-bonding pair of electrons or a lone pair will transition to a pi star orbital, or from pi to pi star. So from this pi bonding orbital, the electron will transition to a pi star antibonding orbital. These are the main two kinds of absorptions that are observed in UV visible spectroscopy. So the UV visible spectroscopy in proteins mainly arises due to the three aromatic amino acids. Most proteins have the absorbance at 280 nanometer compared to nucleic acids, which absorb at 260 nanometer. So the reason for this absorption in proteins are due to the three aromatic amino acids, phenylalanine, tyrosine, and tryptophan. So proteins which lack aromatic amino acids cannot be observed by UV visible spectroscopy, because it is only these amino acids which are giving the UV visible spectrum. So suppose you have a solution which has both nucleic acid as well as protein, then the concentration of protein can be found by this formula, which is 1.55 into the absorption at 280 nanometer, which is basically the absorption due to protein, minus 0.76 into the absorption at 260 nanometer, which is the absorption due to nucleic acid. So using this formula, and the absorbance is detected by the spectrophotometer. So using this formula, you can find the concentration of the protein in mg per ml. The next kind of spectroscopy is known as circular dichroism. So circular dichroism, or CD, is a type of absorption spectroscopy that can provide information on the structures of different biological macromolecules. So there are certain terms that we need to understand before we go into CD. So first is unpolarized electromagnetic radiation. So a light source usually consists of a collection of randomly oriented emitters. That is, the emitted light is a collection of waves with all possible orientations of the electric vector. So we know that electromagnetic radiation has an electric field as well as a magnetic field. So right now we are focusing only on the electric field. In unpolarized light, the electric field can vibrate in many different directions. So there is not a specific direction for its vibration. Polarizer is an instrument that lets the light of a particular direction of vibration pass through it, and it blocks the other directions. So after passing through the polarizer, the unpolarized light becomes unidirectional, meaning that it vibrates in only a single direction. This is called plane polarized electromagnetic radiation, in which the electromagnetic radiation is vibrating in only a single plane. So here this is shown by waves. So the light ray from any source is not polarized. So it can vibrate in the Z direction or in a Y direction. For simplicity, here only two directions are shown. You can imagine the polarizer as kind of a grid, which is allowing only these orange waves or the Z direction waves to pass through it. And it is blocking the other waves. So after passing through the polarizer, the polarized light has only one direction of vibration. The polarization that we learned in the previous slide is plane polarization or line polarization. But the kind of polarization that is important for circular dichroism is known as circular polarization. So circular polarization is a polarization state in which at each point of the electromagnetic field, the wave has a constant magnitude and is rotating at a constant rate in a plane perpendicular to the direction of the wave. So if you imagine these arrows, you can see these black arrows as the direction of vibration of the wave. Then the direction of the vibration of the wave is constantly changing, but the magnitude remains the same. So this is called circular polarization, in which the electric field vector changes its direction constantly, but its magnitude is constant. And it can rotate in one of two possible senses: clockwise or right hand circular polarization. So if you look at this polarization starting from this point, then this is anti-clockwise. So anti-clockwise is also called as left-handed circular polarization, or LHCP, in which the rotation is in an anti-clockwise direction. Or if you look at this one, then this is right-hand circular polarization, because if you start from this point and you rotate, it moves in a clockwise direction. So clockwise direction is also known as right-handed circular polarization. So circular polarization can be of two types, left-handed and right-handed. The principle of CD is that when you pass a light, so light from the light source will generally have the same amount of right and left circular polarization. So it is shown by two different colors, and the right and left circular polarization is equal. After this passes through the optically active sample, there is preferential absorption of this right-handed polarization. There's preferential absorption of this red color, which is the right-handed polarization. So the right-handed polarization component decreases and the left-handed component increases. So CD basically measures the difference between absorption of left and right-handed circularly polarized light. This is measured as a function of wavelength, and after passing through the sample, the left and right beams have different amplitudes. So as you can see, after passing through the sample, the left and right components are unequal, and circular dichroism basically measures the difference between these two components. And this difference is also called ellipticity. So the CD measurement is basically the difference in absorbance of the right-handed and left-handed. So AR minus AL, which is right minus left. And we know from the Lambert-Beer's law that absorbance can be written as epsilon CL, where epsilon is the molar absorptivity. So we are expanding this formula using the Lambert-Beer's law, and we are taking L and C common because the cell is common, so the cell length is common and the concentration is also same. So then you get ER minus EL, which is written as delta E. Here E is the difference in the molar absorptivity or extinction coefficient. So this delta A, or the difference in absorption of the left and right polarized light, is basically what is measured in CD. So in CD, this delta A is actually very small. So if you look at the absorption spectra, which is given in this lower spectrum, the absorption spectra is given in terms of E, or the molar absorptivity, whereas the CD spectra is given in terms of delta E. So according to this formula, the CD spectra depends on delta E, and so that is what is plotted. So delta E is only 3 mole inverse centimeter inverse, but E is 6,000 mole inverse centimeter inverse. So the CD signal, the difference is very small, but the original absorption spectra, the intensity is very high. So in CD, the intensity of the signal is around 0.05% of the original absorption spectra. So we need very sensitive spectrophotometers to measure the CD spectrum. So the CD arises due to the interaction between the different transition dipoles during absorption. So this depends on the relative orientation of the different groups in space, and so the CD signal is very sensitive to conformation. So the CD spectra of different protein secondary structures are very different from one another. So here we have the spectra for polylysine. So basically many lysines are combined together to get a polypeptide chain consisting of only lysines, and that is called polylysines. At different concentrations of buffer, this polylysine chain can adopt an alpha helix conformation, a beta sheet conformation, or a random coil conformation. And depending on that, the CD is different. So as you can see, the alpha helix conformation shown by this blue has a positive peak at 193 nanometer and two negative peaks at 208 and 222 nanometer. The beta sheet will have a positive peak at 195 nanometer and a negative peak at 218 nanometer. And the random coil has a negative peak at 195 nanometer, after which it goes to more or less zero. So these are signature CD spectra for different protein secondary structures. So depending on the secondary structure, you can predict the, so depending on the CD spectra, you can predict the secondary structure of the protein. Here, the general values are given for different protein secondary structures. And if you have an idea of these values, you can find out the secondary structure from the CD spectrum. So CD signals are very sensitive to the secondary structure. So here a protein is taken, which is called GCN4. It is a coiled coil. So there are two different alpha helix, and there are interhelical interactions holding the two helices together. So at 0°C, this conformation is there. This helical conformation is there. And so we are observing the helical signature, which we saw in the previous slide. There will be a peak at 193 nanometer and two negative peaks at 208 and 222. So that is the signature observed, positive peak at 195 and two negative peaks at 208 and 222. So clearly at 0°C, this helical secondary structure is maintained. Now, as the temperature is increased, the helix will start unfolding and eventually it will become a random coil. So as you can see, as you go from 0 to 50 and 75°C, the intensity of the peaks are slowly becoming zero. Eventually at 75°C, the protein completely becomes a random coil, and so it exhibits the spectra of the random coil. Next, if you look at, this is different proteins with different percentages of alpha helices are observed. So myoglobin is completely alpha helical, and so the intensity of the alpha helical peaks are very high. So you can see from 0, if you see the intensity of the peak, the positive peak also has high intensity, and the two negative peaks also have high intensity. Now from myoglobin, if we go to triose phosphate isomerase, which is a mixture of alpha and beta, but predominantly alpha, then the helic intensity decreases a little bit. If we go to lysozyme, in which alpha and beta are more or less equal, you can see that slowly the intensity of alpha helix is decreasing and the characteristic spectra of the beta sheet is appearing. Till we go to chymotrypsin, which is completely beta sheet, and we observe only the characteristic spectra of the beta sheet. So there is progressive change in the intensity as the amount of the helix changes. So the total signal of the protein depends on its secondary structure. For example, if you consider lysozyme, which is a mixture of alpha and beta, it shows the peaks for both alpha and beta. So if you have a protein with unknown secondary structure and you want to calculate that how much percentage of that protein is alpha helix and how much percentage is beta sheet, there is a formula for doing that. So basically, the formula is that theta t, or the observed CD spectra, is x alpha theta alpha plus x beta theta beta plus xc theta c, where x alpha, x beta, and xc are the percentages of alpha helix, beta sheet, and random coil respectively. And theta alpha, theta beta, theta C are the CD signatures of alpha helix, beta sheet, and random coil. So basically what this formula is saying is that the net CD spectra of a protein consists of a certain percentage of alpha helix, beta sheet, and random coil. And now we need to find out what percentage. So this can be done by fitting of the data. So suppose we from X-ray crystallography or NMR, we know that myoglobin has 78% alpha helix and 22% coil. So if you look at this structure of myoglobin, all these green cylindrical portions are alpha helix and these pink portions are random coils. And it comes to 78% helix and 22% coil. And this is obtained from X-ray crystallography. Now, if we want to get this values, the best fitting is when we have X alpha as 80%, or the percentage of alpha helix as 80%, the percentage of beta sheet as 0, and the percentage of random coil is 20%. That is when the experimental and the theoretical prediction is very near to each other. So if you look at this myoglobin structure, the square dots, the dots that are there are the experimental data, and the line that is there is the theoretical prediction obtained from this formula. So they are fitting very nicely, and so the prediction is from CD is reliable. So even here you can see the prediction of CD is that myoglobin is 80% alpha helical, and from X-ray crystallography it was observed to be 78%. So it's quite near to the like the theoretical prediction is very near to the observed value. So like this, CD can be used to calculate the secondary structure composition of an unknown protein. The CD signal also depends somewhat on the environment. So there is a molecule called trifluoroethanol which induces helicity in all peptides. So basically, suppose you have an unfolded peptide and you have trifluoroethanol. What trifluoroethanol will do is that it will form hydrogen bonds with the 4-to-1 stabilizing hydrogen bond in helices. So trifluoroethanol will enhance the helicity by stabilizing the helical hydrogen bonds. So if you add trifluoroethanol to a random coil protein, it will start forming a helix. So if you see the CD spectra of a peptide in water, shown this blue spectra, after adding trifluoroethanol, the peptide becomes much more helical. That is why the intensity of the helical signature is increasing. Similarly, if you have, say, this GCN4 peptide, in the absence of trifluoroethanol, it exists as a coiled-coil structure, which is this blue signal. But in the presence of trifluoroethanol, it dissociates into individual helices. And so the nature of the spectra also changes. So even if both the spectra are helices, coiled coil and single helix will show different spectra. So depending on the environment, the CD spectra is changing. The limitation of this method is that we have assumed that the CD spectra is consisting only of 3 components: alpha helix, beta sheet, and random coil. But this is a very much oversimplification. There can be many different kinds of turns or other secondary structures which are not defined in this formula. And secondly, the shape of the CD curve is also dependent on tertiary structure. So we saw in this plot that even though both are helices, the CD spectra are different. So it is not only the secondary structure, but also the tertiary structure that determines the CD spectra. And that is one of the limitations of this formula, because this formula is only considering secondary structures. So now we will go into fluorescence spectroscopy. Before that, there are certain terms that we need to know. So when a molecule absorbs light, an electron is promoted to a higher excited state. And after, when it is in an excited state, it has to come down to ground state. And it can do this in many different ways. Firstly, the molecule can partially dissipate its energy by undergoing conformational changes and relax to the lowest vibrational level. So this is called vibrational relaxation. So suppose these bold levels that are shown by the bold black lines are the lowest vibrational level. So these four lines together form one electronic level, and within an electronic level, there are several vibrational levels. So this is the S0 electronic level, and in this, there are four vibrational levels. This is the S1 electronic level, and in this, there are four vibrational levels. So from the S0, it can go to any of the vibrational levels of S1. So suppose it goes to the third vibrational level. Then when it comes down from the third to the second, second to the first, like this, that is called vibrational relaxation. So transition within the vibrational levels is known as vibrational relaxation. So, and then when it comes to the lowest vibrational level of S1, it can relax back to S0 in a process called fluorescence. So when it is coming down from S1 to S0, it is emitting an electromagnetic radiation, and this process is called fluorescence. So S0 and S1 are both called singlet states. Singlet basically means that the spin is paired. So in S0, there are two electrons of opposite spin, so the spin is cancelling out. In S1 also, there are two electrons of opposite spin, so the spin is cancelling out, but the two electrons occupy two different energy levels. Now there is something called a triplet state in which the spins are in the same direction, and so they are not cancelling out. So when the spins are parallel to each other, that is called a triplet state, and this is a T1 triplet state. The T1 has four vibrational energy levels. Now, if there is an excited, so if the electron moves from S1 to T1, so it is going from a singlet state to a triplet state. That is known as inter-system crossing. So this line that you can see represents inter-system crossing because it is going from a singlet state to a triplet state. And finally, when it comes down to the ground state from the triplet state, that is known as phosphorescence. So phosphorescence and fluorescence are similar. The only difference is that in fluorescence, the transition occurs between two singlet states. That is, two states where the spins are cancelling out. But in phosphorescence, the transition is from a triplet state to a singlet state. So from parallel spin, it comes to antiparallel spin. This kind of diagram is known as a Jablonski diagram, and it shows the different electronic and vibrational states of a molecule and the transitions between them. So right now we will be focusing only on fluorescence, which is the transition between two singlet states. So in fluorescence, before fluorescence, there must be absorption. So in absorption, the electron is promoted from the ground singlet state to the excited singlet state. Then suppose it goes to the fourth vibrational level of the S1 state. Then there can be a certain energy loss by vibrational relaxation, where it will come down to the lowest vibrational level of the S1 state. And after that, there will be fluorescence back to the S0 state. So because there is a certain loss in energy due to this vibrational energy loss by collision with the solvent, the energy that is emitted in fluorescence is lower than the energy that was absorbed during absorption. So if you see the peak, so the peak of absorption has lower absorption is shown by this black line. So the peak of absorption has lower wavelength, meaning higher energy, and the peak of fluorescence has higher wavelength, meaning lower energy. So the fluorescence peak will have lower energy because a certain amount of energy is lost by these vibrational relaxation, where the transition is occurring from higher vibrational level to lower vibrational level. Now, the difference between the peak of absorption and fluorescence is called as a Stokes shift. So Stokes shift is the gap between the maximum of the absorption band and the fluorescence band. Another thing to note is that the spacing of the vibrational level of the excited state is similar to that of the ground state. So the fluorescence spectra is always a mirror image of the absorption spectrum. And you can also remember the lifetime of the different states. So the lifetime of the excited S1 state is 10 to the power minus 10 to 10 to the power minus 7 seconds. So this is also the time scale of fluorescence spectroscopy. So the time difference between absorption and fluorescence is around 10 to the power minus 10 to 10 to the power minus 7 seconds. So it is a very short time scale, like nanosecond time scale, and that is the lifetime of this excited energy state. So there are certain terms that we need to learn in relation to fluorescence. One is called the quantum yield, represented by phi f. So this is the ratio of the number of photons emitted to the number of photons absorbed. So the number of photons absorbed is always higher, and so quantum yield is always less than 1. The second term is the lifetime of the excited state tau. Tau is defined, this is the average time that the molecule spends in the excited state before returning to the ground state. So suppose the molecule is promoted from S0 to the S1 excited state. The energy can be released in two kinds of ways. One is the non-radiative transition, where shown by these red arrows, where there is transition between the different vibrational energy levels. And this energy is mainly lost as heat. So when the molecule collides with other molecules or with solvent molecules, the loss of energy as heat due to these collisions are the non-radiative transitions. And then the transition can occur from S1 to S0 in the form of fluorescence, which is a radiative transition. So the lifetime is defined as 1 by eta plus KNR, where eta is the emissive rate of fluorescence and KNR is the rate of the non-radiative transition. So the lifetime of the excited state depends on the rate of fluorescence as well as the rate of this transition. When the rate is large, the denominator becomes large, and so the lifetime becomes small. The natural lifetime is basically the lifetime of the fluorophore in absence of these radiative transitions. So in natural lifetime tau n, KNR is 0 and tau n becomes 1 by eta. So the larger the rate of the decay of the radiation, the smaller is the lifetime of the excited state. So the instrumental setup of fluorescence is similar to that of the spectrophotometers that we had observed, but the spectrum can be of two different types. One is the emission spectrum, in which the excitation wavelength is kept constant and fluorescent intensity is measured as a function of wavelength. So the excitation spectrum is shown by the blue line here, in which the wavelength that is used for So in excitation spectrum, the wavelength that is used for excitation is constant, and we observe the emitted fluorescence spectrum. And in emission spectrum, fluorescence intensity at a particular wavelength is measured as a function of the excitation wavelength. So excitation and emission spectrum is kind of like absorption and emission. So as we had learned previously, the wavelength of, so we saw from Stokes shift, the wavelength of absorption is always lower than the wavelength of fluorescence. So that is why the wavelength of the excitation spectrum is smaller than the wavelength of the emission spectrum. Now, suppose this is a peak, and the peak, due to some chemical change, the fluorescence peak is shifting to lower wavelength. That is called a hypsochromic or blue shift. Again, due to some chemical change, if the peak shifts to higher wavelength, that is called a bathochromic or red shift. If the intensity of the peak increases, that is a hyperchromic shift. And if the intensity decreases, that is a hypochromic shift. So these are some terms that you need to remember. So solvent has a large effect on fluorescence spectra. Generally, the fluorophore has a larger dipole moment in the excited state compared to the ground state. So if you have a more polar solvent, it will stabilize the excited state more compared to a less polar solvent. So in simpler terms, the dipole moment of the excited state is high. So in a polar solvent, the excited state becomes stabilized and its energy decreases, while in less polar solvent, the excited state has higher energy. So if in a polar solvent, you have an S1 to S0 transition, the energy released is lower, meaning that the wavelength will be higher. So the example is shown here, where this is a fluorescence spectra recorded in 100% heptane, and then the percentage of heptane is decreased to 90%, 80%, till it eventually becomes 100% water. So this is for a heptane water mixture from 100% heptane to 100% water. So as the polarity of the mixture increases, meaning the percentage of water increases, the wavelength of fluorescence also increases. And increase in wavelength means decrease in energy. So this explains the effect of polar solvents. So in polar solvents, the wavelength of this peak will increase to larger wavelengths. Again, fluorescence spectra of some molecules are very sensitive to pH due to an equilibrium between protonated and deprotonated form of the fluorophore. So if you look at this particular fluorescence spectra at different pH, so pH has been changed from 5 to 6 to 7 to 9. The fluorescence spectra is also changing. So fluorescence can also be used as an indicator of pH. So looking at that particular spectra, we can predict what is the pH of the solution. Now there is something called fluorescence quenching. Fluorescence quenching refers to any process that decreases the fluorescence intensity of a sample. There are two kinds of fluorescence quenching. One is the collisional or dynamic quenching. So collisional or dynamic quenching occurs when the excited fluorophore experiences contact with an atom or molecule that can facilitate non-radiative transition to the ground state. So suppose this is your fluorophore. There is a light falling on the fluorophore. What it does is that the fluorophore will transfer the energy to the quencher, and the fluorophore will return to the ground state. So this is a method of non-radiative quenching, and it basically occurs with collision with the quencher. So common quenchers are oxygen, iodide, and acrylamide. So when the fluorophore collides with, say, the oxygen molecule, it will transfer the energy to the oxygen molecule. And in this way, the fluorophore will return to the ground state. Since the energy transfer is occurring due to collision, due to movement of the molecules, it is called a collisional or dynamic quenching. So here you can see naphthalene colliding with a quencher like, say, iodide. And so this is excited naphthalene. After collision with the quencher, it will transfer the energy to the quencher and go back to the ground state. In the case of collisional quenching, there is an equation called Stern-Volmer equation, which is F0 by F is 1 plus KSV into concentration Q. So F0 and F are the fluorescence intensity observed in the absence and presence of the quencher. So when the quencher is not present, the fluorescence intensity is F0, and in the presence of the quencher, the fluorescence intensity is F. KSV is the Stern-Volmer quenching constant, and Q is the quencher concentration. So if you have a plot of F0 by F with the concentration of the quencher, then the slope of the plot will be KSV and the intercept will be 1. KSV can also be written as KQ tau 0, where KQ is the bimolecular quenching rate constant and tau 0 is the excited state lifetime in the absence of quencher. For pure collisional quenching, F0 by F can be written as tau 0 by tau. So basically, tau 0 is the lifetime in the absence of quencher and tau is the lifetime in the presence of the quencher. Tau 0 by tau can be replaced by F0 by F can be replaced by tau 0 by tau, and KSV can be expanded by writing KQ tau 0, which gives this equation. So this is the Stern-Volmer equation in case of collisional or dynamic quenching. The second kind of quenching is known as static quenching. In static quenching, the fluorophore can form a stable complex with another molecule. If the ground state is non-fluorescent, then we say the fluorophore has been statically quenched. So basically, this is the free fluorophore. It forms a complex with the molecule. So this is the fluorophore ground state. After absorption of the energy, it gets promoted to the fluorophore excited state. After binding with the quencher, it goes to the fluorophore quencher complex, and then non-radiatively, the energy is released and the fluorophore quencher complex goes to the ground state. So there is an equilibrium between the association of the fluorophore with the quencher. And in this case, the Stern-Volmer equation becomes F0 by F, where F0 is the fluorescence intensity in absence of the quencher and F is the intensity in presence of the quencher. So F0 by F is 1 plus KAQ, where Ka is the association constant of the FQ complex and Q is the quencher concentration. So in static quenching, basically the free fluorophore emits fluorescence. But once it couples with the quencher, the fluorophore quencher complex does not have any fluorescence. So fluorescence is quenched when the complex is formed. Static quenching will not reduce the lifetime of the sample. Normal excited state properties. And so the lifetime remains the same in static quenching because not 100% of the fluorescence molecules are forming complex. The fluorophore molecules which are not forming the complex will have the same lifetime. However, the intensity of fluorescence will decrease because initially 100% of the F molecules were emitting fluorescence. But after formation of the complex, those molecules that are in the complex do not have any fluorescence. So the intensity of the fluorescence is decreasing in static quenching. Now, if a molecule has both static and dynamic quenching, then this equation and the previous equation are combined, and the net equation becomes F0 by F is a product of the two equations that we studied. So 1 plus Kq tau 0 concentration Q into 1 plus Ka concentration Q. So that is when both static and dynamic quenching is present. Next, we will go into Forster's resonance energy transfer, or FRET. So fluorescence emission from donor D. Suppose you have a photon which is exciting the donor D molecule to an excited state. Then donor D is emitting an energy that is absorbed by the acceptor A. So the emission spectrum of the donor and the absorption spectrum of the acceptor must overlap. So basically what happens is that in normal fluorescence, the donor will absorb the proton and then release fluorescence. But in this case, the fluorescence of the donor is not observed because the energy released by the donor is accepted by the acceptor, which then releases fluorescence. So the fluorescence spectra is observed for the acceptor, and the emissions excitation spectra is observed for the donor. FRET is a non-radiative process. The FRET efficiency is dependent on the distance between donor and acceptor. So the distance between donor and acceptor must be less than equal to 10 nanometer. Only then the energy can be transferred from donor to acceptor. And the dependence of the energy emitted on the distance is by this formula, which is basically dependent on r to the power -6. Again, if we look at the angular dependence, if the donor and acceptor are at 90 degrees to each other, then the energy cannot be transferred. At any other angle, the energy can be easily transferred and FRET is observed. So the reason that the donor emission and the acceptor excitation must overlap is that only when there is an overlap, the energy emitted is similar to the energy required for excitation, and then FRET can occur. So the general fluorophores in proteins include the aromatic amino acids like tryptophan, tyrosine, and phenylalanine. But the major contributor is tryptophan. So a protein can have just 1 or 2 tryptophan residues, and that is enough to observe the spectral changes in the protein. So suppose we want to study the mechanism of folding of the protein. So if we attach a tryptophan to the protein, we can, from the fluorescence spectra of the tryptophan, we can observe that what are the conformational changes happening in the protein. And from that, we can predict that what is the folding mechanism. If you look at the, this is the quantum yield. So you can see that the quantum yield of tryptophan is 0.2, which is greater than tyrosine or phenylalanine. This basically means that the intensity of the fluorescence spectra for tryptophan is the highest. And so tryptophan is the most dominant fluorophore in proteins. A protein which shows a lot of fluorescence is the green fluorescence protein, or GFP. It is composed of 238 amino acids, and each monomer has a central alpha helix surrounded by an 11-stranded cylinder of anti-parallel beta sheet. So this kind of secondary structure is formed in which there is a central alpha helix and a cylinder of beta sheet. And in the middle of this structure, the fluorophore is located. So the fluorophore basically consists of serine, tyrosine, glycine. So when this tripeptide is present, serine, tyrosine, glycine, an autocatalytic cyclization can occur to form this particular moiety. And this moiety has a lot of conjugated double bonds, meaning double, single, alternating double and single bonds. And this allows intense fluorescence to occur. There are many mutational variants of the green fluorescent protein, which can give fluorescence of different colors. Like EGFP is also green color, but the fluorescence is enhanced a lot. In EGFP, the serine is replaced by a threonine. Glycine and tyrosine remain the same, but serine is replaced by threonine, and this results in fluorescence which is green in color but of much higher intensity compared to native GFP. Again, you can replace tyrosine by a histidine, and that will give dark blue colored fluorescence. Similarly, there are other mutations which can cause different colors of fluorescence. Just give me 1 minute. So now we will move to IR spectroscopy. We had studied earlier that IR spectroscopy it mainly causes vibrational transitions in the molecule, and it is used to determine the functional groups. Now the IR region, it can be divided into three parts. Near IR, which is from 0.8 to 3 micrometer, mid IR from 3 to 8 micrometer, and far IR from 8 to 15 micrometer. Most of the applications are confined to the mid IR region because most of the functional groups in chemistry are excited by the mid IR region. So IR spectroscopy detects the different kinds of vibrations. So we look into the different kind of vibrations possible in a molecule. First is stretching vibration. There can be symmetric stretching in which, so suppose this is a molecule like water, H2O. Symmetric stretching is when both the bonds stretch equally outwards then inwards at the same time. Asymmetric stretching is when one of the bonds stretch outwards and one of them stretch inwards. So it is asymmetric. Bending vibrations can also be of different types. So in-plane bending is of two types. Scissoring, where the movement is like a scissor. Both the bonds move inwards, then outwards. Both move together inwards, together outwards. Rocking is when both move first towards the left, then towards the right. So when both the bonds move together towards the left, then together towards the right, that is rocking. Out of plane movement, twisting is basically this bond moves outwards. So if you imagine the slide as a plane, this bond is moving in the upward direction and this is moving in the downward direction. So that is called twisting, when both the bonds move in opposite directions. And wagging is when both the bonds move in the same direction. So both are moving upwards or both are moving downwards. So these are the different kinds of vibrations that are detected by IR spectroscopy, but the most useful ones are the stretching vibrations. So in IR spectroscopy, there can be two kinds of spectras. Absorbance, which shows that which wavelengths are absorbed, or transmittance, which is shows that which wavelengths are really emitted. So absorbance and transmittance are kind of like a mirror image to each other because those wavelengths that are absorbed are also emitted. Normally, the IR spectra is given in the form of transmittance spectra, where the percentage transmittance is plotted in the y-axis from 0 to 100. So 100% transmittance means that there is no absorption. So there is no functional group. And as the transmittance decreases, that means there is some group which is absorbing the wavelength. And in x-axis, wave number is plotted. IR bands can be classified as strong, which have almost zero transmittance, medium, and weak. So there are three kinds of intensities in IR bands. IR bands can also have a broad signal which encompasses many different wave numbers, or a narrow signal pointing to a single wave number. Now, not all covalent bonds display IR bands. Only polar bonds are IR active. Non-polar bonds can also be IR active if the dipole moment changes. So suppose you have a CO2 molecule. Now, if there is symmetric stretching, that means both are stretching outwards, then both bonds are stretching inwards. Then the dipole moment is cancelling out, and so that is this is IR inactive. But if there is asymmetric stretching, so one bond is stretching outwards and one bond is stretching inwards. So the length of the bonds become different, and so the molecule has a net dipole moment. Since the molecule has a net dipole moment, the asymmetric stretching becomes IR active. Now, if the polarity is high, like the carbonyl groups, then a strong IR band is observed. If the polarity is medium, like the nitrile or cyanide group, a medium intensity band is observed. And if the polarity is very weak, like this alkyne, unsymmetrical alkyne, then a weak IR band is observed. But in case of a symmetrical alkyne, like this one, there is no net dipole moment, and so IR is not observed. These are the characteristic IR frequencies of different functional groups, and you can remember the main ones like the carbonyl and the alcohol and the nitrile, and this will help you interpret the spectra. We will look into some example IR spectras. So this is the IR of different carbonyl compounds. One is aldehyde, which is a CHO group. This is ketone, which is a CO surrounded by C on both sides. And this is a carboxylic acid, which is COOH. So in case of all three, the CO stretching is observed. If you look at this peak at 1720, 1718, or 1711, so the CO stretch is observed in all three because all three have a C double bond O. But the additional thing in aldehyde is the CH stretching. So this region is the CH stretching. CH stretching. These two peaks, 2820 and 2720, are the CH stretch, which is observed in aldehyde but not in ketone because ketone does not have a CHO. And in acid, an extra OH signal is observed because the acid has an OH. So even if all three have the C double bond O stretching band, only the acid will have the OH broad band because the acid has a COOH group, and only the aldehyde will have a CH stretching from the CHO. So like this, the ketone, aldehyde, and acid can be differentiated. Then different kind of amine will give different signals. So if you have a primary amine, which is NH2, there are two NH bonds, and so there are two peaks for the two NH bonds. Secondary amine has only one NH bond, and so there is a single peak. In tertiary amine, there is no NH, so there will be no peak for the NH. Similarly, in primary amide or CONH2, there are two peaks for the two NH bonds. In secondary amide, there is only one NH, so there is one peak. And tertiary amide, there is no NH, so there is no band for the NH stretch. So you can differentiate between primary, secondary, and tertiary amines and amides. There are different applications of IR spectra. First is detection of solvents. So suppose you have an unknown solvent, you can match the IR spectra of the unknown solvent with the IR spectra of common solvents that are reported in literature. So like that, you can find out that what is the unknown solvent. Similarly, if you have an unknown sample, you can compare the unknown sample with the known IR spectras of common compounds, and you can find out what is the unknown compound. Again, the determination of contaminants in air can be found out by IR. So contaminants like carbon monoxide, ethylene oxide, and methanol, their concentration can be found based on the intensity of the IR peaks. So if the IR spectra is taken for air, and based on the relative intensity, the concentration of each of the constituents can be found. And this has been found to be very accurate, with percentage error only being around 1.8 or 1%. A special kind of IR, which is generally used in the laboratory, is called Fourier transform IR spectroscopy, or FTIR. So in FTIR, what happens? There is a Fourier transformation to convert the interferogram or the raw data into the actual spectrum that we observe. The advantage of FTIR is that compared to normal IR, the resolution is very high and a large spectral range can be collected. So FTIR provides information about the secondary structure of the proteins. So up to now, we have seen that X-ray crystallography and NMR gives us information about the tertiary structure of proteins, but FTIR tells us only about the secondary structure. For example, there are characteristic bands called amide 1 and amide 2 that are found in amino acids. So you know that amino acids are connected by amide bonds to form a polypeptide, which eventually form proteins. So in this amide bond, there is amide 1 and amide 2 stretching frequencies. And amide 1 is specially important because the amide 1 signature differs according to the secondary structure. So for alpha helix, you can see that there is a broad band at around 1660 centimeter inverse for the amide 1. The beta sheet has a broad band around 1620. So if you remember the characteristic values for the different secondary structures, you can find out from the IR spectra that what is the secondary structure of the protein. So this is the final kind of spectroscopy that we will learn today, which is Raman spectroscopy. So in Raman scattering, what happens is that there is an incident light from the laser on the molecule, and there is a certain fraction. So there are two kinds of Raman scattering, Stokes and anti-Stokes. In Stokes, what happens is that there is absorption, and then the emitted energy is lower than the absorption energy. That is, the emitted wavelength is higher. In anti-Stokes, the opposite happens. So the absorbed wavelength is lower than the, the absorbed wavelength is higher than the emitted wavelength. So Raman, so this is the first kind of scattering spectroscopy. So far, what we have seen in IR and UV visible is that the molecule is absorbing the energy and then emitting it. But Raman is a kind of scattering spectroscopy where you can see that a small fraction of the scattered light has a different color. So if a certain wavelength is incident, then the emitted wavelength is slightly different. And this difference is caused by the light interacting with the molecular vibrations. And this is Raman scattering. So the normal kind of scattering, which is Rayleigh scattering, is called elastic scattering because there is no energy loss. Whatever is the energy of the incident light, that is the energy of the scattered light, and that is Rayleigh scattering. But in Raman scattering, the energy of the scattered light can either be lower, which is called Stokes Raman scattering, or higher, which is called anti-Stokes Raman scattering. The Raman scattering effect is very weak. So if there are 10 million photons, only one photon will undergo Raman scattering. So a very sensitive spectrometer is needed. Raman scattering is generally used to observe vibrational, rotational, and other low frequency modes in a system. So if you compare IR and Raman spectroscopy, there are certain differences. Firstly, IR is the result of absorption of light, but Raman is the result of scattering of light. In IR, the intensity of the peak is related to change in dipole moment. So if you have a compound with strong dipole moment, like a carbonyl compound, the IR intensity will be high. And if the dipole moment is zero, like a symmetrical alkyne, the IR intensity will be zero. But in Raman, the intensity is related to the polarizability of the stretch. That means non-polar bonds usually show Raman spectroscopy. And finally, IR only works in the infrared region of the spectrum, but Raman can work in the visible near infrared or near UV range. There is a simple rule to remember that for symmetric molecules, IR active vibrations are not Raman active, and Raman active vibrations are not IR active. So the example of CO2 is shown here, where in the equilibrium structure, the dipole moment is zero and the polarizability is also zero. So both Raman and IR are not observed. Now, if there is a symmetric stretching, we learned that in symmetric stretching, the dipole moment is zero, so it is IR inactive, but it is Raman active. Then in asymmetric stretching, we studied that the dipole moment is changing in asymmetric stretching, so it is IR active, and that makes it Raman inactive. Again, in bending, the dipole moment is changing, so it is IR active, and IR active means Raman inactive. So there are several advantages of Raman over IR. Firstly, Raman can be done in water, and so biological samples can be easily studied because the main biological solvent is water. Next, completely symmetric vibrations are observable. So if you think about the symmetric stretching, we cannot observe it by any other spectroscopy except Raman spectroscopy. And secondly, finally, the Raman intensities are proportional to concentration and laser power. So you can easily increase the intensity by increasing the concentration or the power of the laser that you're using to observe it. There are different kinds of Raman spectroscopy. The first kind is resonance Raman. So in this one, the excitation wavelength is carefully chosen to be very close to that of electronic transition. So basically, in normal Raman spectroscopy, the absorption can be of any energy. But in resonance Raman, such energy is chosen that the molecule can undergo an excitation to the higher electronic state. The frequency coincidence or resonance can lead to greatly enhanced intensity of Raman scattering. So if there is a transition to a higher electronic state, when Raman occurs under this condition, the intensity is highly increased. And so even if we have a sample of low concentration, we can study it using resonance Raman spectroscopy because this greatly increases the intensity by 10 square to 10 to the power 6 times. Another is surface enhanced Raman spectroscopy or SERS. So in this, what happens? The intensity of Raman spectroscopy is enhanced by molecules on the surface. Like it can be a metal surface or a nanostructure surface. So when there is Raman scattering from this special surface, the intensity increases up to as much as 10 to the power 10 to 10 to the power 11 times. And this increase in intensity enables us to detect even a single molecule. So Raman spectroscopy for proteins. As we have seen in IR, the amide 1 has certain characteristic peaks for each secondary structure. The same is for Raman. So amide 1 band in Raman is mainly from the CO stretch, and it comes around 1650 centimeter inverse. But the speciality of this is that different secondary structures are characterized by the amide band being in different positions. So if we look at the lambda max of the peak, we can predict what is the secondary structure of the protein from the amide 1 band in the Raman spectrum. The amide 3 band also is less important, but it also is different for different kinds of secondary structures. Like for alpha helix, the amide 3 band comes at 1298, for random coil at 1250, and for the beta sheet, it comes at around 1232. So from the amide 3 band also, the secondary structure can be predicted. Raman spectroscopy can also be used to detect the presence of disulfide bridges. So if there are two cysteine molecules, a disulfide bridge can form, and the characteristic of the disulfide bridge is a peak which appears from 500 to 550 centimeter inverse. So we can find out if the two cysteines are free or they are connected by a disulfide bridge. Again, aromatic amino acids have very characteristic Raman spectroscopy. Like phenylalanine has one intense peak at 1000 centimeter inverse. Tyrosine has two peaks at 830 and 850. And tryptophan has two peaks at 1340 and 1360. So, can you please mute yourself? Yeah, so Raman spectroscopy is also characteristic for the different aromatic amino acids. We will finally go into two applications of Raman spectroscopy. One is called Raman microscopy. So in Raman microscopy, basically, a microscope is connected with the Raman spectroscopic setup. So what happens is that you can highly magnify a sample and then carry out Raman spectroscopy on that sample. So the principle is quite easy. So the microscope will focus on the sample and it will enlarge the visualization of the sample. After that, laser is passed through that enlarged, like we can easily visualize the sample, and then the laser can be passed through the sample to carry out Raman spectroscopy, which is detected. So this microscope is that is normally used is called a confocal microscope, and it can easily help to identify the X, Y, and Z axis of the sample. So what this does is that if you have a very microscopic amount of sample and you want to do the Raman spectroscopy for that sample, you can focus on the sample using the microscope, and you can figure out where to excite using the Raman laser light. And like that, even if you have a very small amount of the sample, you can observe it using Raman microscopy. Another application is called Raman crystallography. So Raman spectroscopy can be used to compare the conformation of proteins in solution with those in single crystals. So what is done here is that if you have a single protein crystal, so we had learned about the hanging drop experiment where the protein is crystallized out from a solution of the protein and the co-crystallization solvent. So if we want to study what is happening in the crystal, then the Raman spectroscopy can be used to focus the Raman laser light on that crystal. So what this will help us to do that, suppose we are co-crystallizing a protein molecule, suppose an enzyme and its inhibitor. So we want to find out that what is the mechanism by which the inhibitor is inhibiting the enzyme. So one way of doing this is co-crystallizing the inhibitor and enzyme. So when the enzyme and inhibitor are co-crystallizing, um, we want to look deeply into the crystal to find out what is happening. So that can be done by allowing the protein and crystal to crystallize on this hanging drop and then focusing the Raman spectroscopy on the crystal. So from the change in Raman spectroscopic data, we can find out that what are the conformational changes happening in the enzyme due to interaction with the inhibitor. So Raman crystallography can be used to study what are the mechanisms happening inside a single crystal. So in this, what is done is single protein crystals are mounted in a cuvette or glass vial and positioned at the focal point of the Ford optics, that is at the front of a standard Raman instrument. So you have the Raman instrument and you're focusing the Raman spectroscopy on that particular crystal, single crystal that is forming. So it allows you to follow chemical changes within that single crystal in a manner that is similar to X-ray crystallographic analysis. There are advantages of Raman over X-ray crystallography. That is, firstly, high signal to noise ratio. Next, in X-ray crystallography, since you are adding X-rays, there can be a lot of disturbance of the sample, but and background light. But this is all excluded in Raman spectroscopy. And secondly, you can easily compare what is happening in the single crystal compared to what is happening in solution using the Raman crystallography. So this brings us to the we have talked about two applications in short of Raman spectroscopy, which is Raman microscopy and Raman crystallography. So that brings us to the summary of week 7. Now we'll just go through a few sample questions. So first is that, which is the significant peak of an alpha helix in CD spectroscopy? So the answer to this is D, or 222 nanometer. So if you remember the spectra of polylysine that we studied in different conditions, so the characteristic peak of an alpha helix is a positive peak at 193 and two negative peaks at 208 and 222 nanometer. So since 193 or 208 is not there in the option, the only correct answer is 222 nanometer. The second question is that chemical events within the crystal can be obtained from which of the following technique? So the answer to this is D, Raman crystallography. So as we studied, one of the applications of Raman spectroscopy is Raman crystallography, in which what happens is that a crystal is formed using the hanging drop method, where there is a equilibrium between the crystal and the protein solution. So as the crystal is forming, you have to focus the Raman spectroscopic incident light on the crystal so that the Raman scattered light that is obtained and the spectra that is formed will give us an idea of what is happening inside the crystal. So if we have, and as I said, if we have an enzyme and an inhibitor of the enzyme, and we want to find out how the inhibitor is stopping the enzyme activity, then we can co-crystallize the enzyme and inhibitor. And through Raman crystallography, we can observe the chemical changes happening inside the crystal. So Raman crystallography is the method using which chemical events within a crystal can be studied. The next question is calculate the Stokes shift of a molecule that has excitation and emission wavelengths at 280 and 340 nanometer respectively. Right, so the answer of this is C. So the formula for calculating the Stokes shift is taking the difference in wavelength of the emission minus the absorption. Or in terms of, as we know, the emission spectra has larger wavelength or lower energy compared to the absorption spectra, because some of the energy is lost with due to collision with other molecules or with molecules of the solvent. And Stokes shift refers to the difference in wavelength calculated by the difference. So we have to take the maximum, the wavelength at the peak of the spectra for emission minus the wavelength at the peak of the spectra for absorption. So emission is 340 minus 280 will give you 60 nanometer, which is answer C. Sample question 4 asks, which mutation in wild type GFP or green fluorescent protein is responsible for the enhanced phenotype EGFP or enhanced green fluorescence protein? So the answer of this is A. So if you remember the green fluorescent protein, the chromophore is serine, glycine, tyrosine, this tripeptide. And there is a mutation called EGFP or enhanced green fluorescent protein, where the serine is mutated to a threonine. Glycine and tyrosine remain the same, but the serine at the position 65 is mutated to threonine. So the mutation is S65T. S because originally it was serine, 65 is the position, and after mutation it is threonine, so T. So the correct answer is A. In EGFP, the color of the fluorescence remains green, but the fluorescence intensity is enhanced a lot. So this is one of the useful mutations of green fluorescence protein. Question 5 is identify the correct order of increasing wavelength in the electromagnetic spectrum. So the correct answer is B. If you remember the electromagnetic spectrum, the highest wavelength is indeed that of radio waves, and followed by infrared, visible, ultraviolet, then X-rays. So the correct answer is B. What is the unit of absorbance is the question. Next question. So the answer is D. If you remember the formula of absorbance, it is log of the ratio of I0 by I, where I0 is the intensity of light entering the sample and I is the intensity of light leaving the sample. So since it is a ratio of intensities, the units of intensity will cancel out and absorbance will have no unit. So the correct answer is D. Sample question 7 asks, what is the unit of ellipticity in CD spectroscopy? So the correct answer is B, millidegrees. So if you remember, CD signal is the difference in absorption between the left and right circularly polarized light. So before entering the optically active sample, the left and right components of circularly polarized light are equal. But after exiting the sample, there is bias towards either the left or the right direction, and that difference is recorded as CD spectroscopy, in which the x-axis is always wavelength and the y-axis is called the ellipticity, measured in units of millidegrees. So the correct answer is B. The eighth question is that what is the relationship between the intensity of light with sample concentration in Beer-Lambert's law? So the answer here is proportional. So absorbance is equal to epsilon LC, where epsilon is the molar absorptivity, L is the path length, and C is the concentration. So absorbance is directly proportional to the concentration. So if you plot absorbance and concentration, you will get a straight line uh, in which the slope is equal to the product of epsilon L and the intercept is 0. The next question is that molar extinction coefficient of a molecule is dependent on which parameter? So the correct answer is C, wavelength. Sorry. Yeah. So for a particular molecule, if the wavelength of the incident radiation is changed, then the molar extinction coefficient changes. So it is dependent on wavelength that is used by the source light. The last question for today is that which amino acid residues in a protein molecule are responsible for the absorbance maximum at 280 nanometer? So the correct answer is A. So if you remember that in the UV of protein is due to the presence of the aromatic amino acids, and they show a characteristic absorbance around 280 nanometer. So if a protein does not have an aromatic amino acid, we cannot observe it using UV visible spectroscopy. So that is all the questions for today. So if there are any doubts, you can mail me regarding them, or you can
Ma'am,
ask. Huh? Yes.
hello, ma'am.
Yes.
Ma'am, can you like why intensity is directly proportional to the concentration? Like the absorbance is directly proportional, but I think intensity is the inversely proportional, because if concentration increases, intensity of transmitted light will be decreased.
Okay, so see, in Lambert-Beer's law, uh, it is talking about Lambert-Beer's law. So Lambert-Beer's law is for UV visible spectroscopy. And in UV visible spectroscopy, we observe the absorbance. So if you look at the UV visible spectroscopy, we in the y-axis, absorbance is there. You're thinking about infrared spectroscopy, where in the y-axis, transmittance is there. So when it is talking about intensity of light in UV visible spectroscopy, we are talking about absorbance. That is why it is proportional.
Okay, ma'am. Okay, thank you.
Mhm. Okay. So any other questions? So if you have any questions before the next class, you can email me before Monday so that I can prepare slides for the answers to your questions. And that will be all for today.